All right. So section 7.1 is logic. We're going to define propositions and connectives, build truth tables, define converse and contrapositive, construct compound truth tables, and discuss logical equivalence and logical implication. All right. So first up is the definition of a proposition. A proposition is a statement that is either true or false. No iffiness about the statement itself. The statement is either true or it is false. So, for example, how about this statement? Odie is a dog. Is that a proposition? Yes, because Odie is a dog. That's either true or it is false. Odie is either dog or he is not a dog. That is a true or false statement, right? And y'all know who I'm talking about, right? Odie and Garfield is a giraffe. Is that a proposition? Yes. That is a proposition. It is either true or false that Garfield is a giraffe. All right. And by the way, which are these? Odie is a dog, true or false? That is true. Odie is a dog. And Garfield is a giraffe, true or false? That is false because Garfield is a cat. Okay. So these are from the comic books, right? Okay. All right. All right. What kind of letters do we use to denote propositions? Lowercase. Lowercase letters. So, for example, and they usually start with P's. They're in the P range here. P, Q, R, S, T. These are usually the letters that they use for propositions. There's sort of a hierarchy to letters. Just like, you know how you use F, G, and H for functions, X, Y, and Z for variables, A, B, and C for constants. Yeah, the P range is the proposition range. So the proposition little p right here would be, maybe, Odie is a dog. Oops, is a dog. So that proposition would be little p. And you can make up one for the other one as well. All right. Now, connectives are used to sort of make bigger propositions, right? And we have symbols for each of these. The first one is negation or negative, and the symbol for that it's not quite a minus sign. It's a dash with a little downward hook at the end. Okay, and so maybe we have not P. Okay, so that we would read this as not P. And of course, not P would be whatever the opposite of P is. And we're gonna give more examples of these as we go through. But we're just going to make the whole table right now. Disjunction is between two different propositions. So we have P or Q. And the symbol for or is, it's like a V, but it's not a V. It's more straight up and down like that. And this is P or Q. Conjunction, what do you think conjunction is? If disjunction was or, what is conjunction? And, yeah. And the symbol for and is the reverse of that, or the upside down version of the or symbol. So this is P and Q. And then conditional is P with an arrow going over to the Q. And we read this one as if P, then Q. So there's our 4 connectives. Now we need to know how to work with each of these, and so we'll do that one at a time. And first up is negation. Okay. So we're going to start with P. Now, what are the 2 possible starting statuses P could have? P is a proposition, so P is either true or it is false. We'll use a capital T for true and a capital F for false. What I'm doing here is I'm sort of loading up the table. Okay? This is called a truth table. And we're going to start with proposition P, and we're going to acknowledge that P is either true or it is false. If I want the negation of P is the opposite of the truth value of P itself. So if P is true, then what is not P? And not P is false. And if P is false, then what is not P? It is true. Okay? So that's how you alter the values of a proposition. If it is negation, then it is the opposite value. True becomes false, and false becomes true. Let's do an example here. Let's start with P, the proposition that Odie is a dog. In English, what is the proposition not P? Odie is not a dog. The proposition that Odie is a dog was true or false? True. It's true. And the proposition not P, that Odie is not a dog, is false. False. Because Odie is a dog. Questions over negation? All right. Let's look at disjunction. Disjunction symbol is P or Q, and this is true when at least one is true. So a disjunction starts with 2 propositions, P and Q, and then P or Q right here. I need to seed the table. What are all of the possible ways that P and Q could start out as? Not knowing anything else about P and Q, just general P and Q. They could both be true, right? So P is true and Q is true. What else could happen if P is true? Q could be false. Perhaps it is the case that P is false while Q is true. And the last scenario is what? You're both false. Okay. Now, disjunction is or. So let's put that here in sort of super letters here. Now, this is math or. This is not normal vernacular or. Okay? If you go to your friend and you say, let's go to McDonald's or Taco Bell, then presumably you only go to one of those. You either go to McDonald's or you go to Taco Bell. That's a different or than this or. This or does not preclude the possibility that you go to both of them. All right? You get a Big Mac and a taco. Okay? All right. So that's why it's written this way. At least one is true makes this proposition true. So here, P is true, Q is true, P or Q is true because at least one of them was true. In fact, they were both true, which is fine. What about the second line? P is true, Q is false. That is true because at least one of them was true. Q is false and P is false and Q is true. That would be true. And then if they're both false, then what is the result? The proposition is false. Yeah. P or Q is also false. So the only way that P or Q could be false is if both the propositions start off as false. That's it. Okay. So let's use P and Q from before. So starting off with P, that Odie is a dog. And Q, Garfield, is a giraffe. Let's form the proposition P or Q in English. So what would this be? Odie is a dog, or Garfield is a giraffe. All right, Odie is a dog. True or false? True. Garfield is a giraffe. True or false? False. The proposition Odie is a dog or Garfield is a giraffe. That is true. Yeah, because one of the propositions forming that one was in fact true. All right. Questions so far? All right. Next up is conjunction. Conjunction is and. So we have P and Q. And by the way, there's a neat little way to remember which symbol is and which one is or at least which one is and. The and symbol looks like an A without the horizontal bar. There, just a little A right there. In order to get a conjunction to be true, then all must be true. If any of the statements are false, the conjunction statement is false. Okay. So let's load up the table. So P, Q, P, and Q. And we're going to start with our basic truth table. True, 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 false, false, true, and false, false. All right, if P is true and Q is true, then what do we know about P and Q? It is true, because all of the statements were true. If P is true and Q is false, what do we know about the conjunction? False. And what about the next one? False. And the next one? False. That one is false. Yeah. So in order for it to be true, all of them have to be true not they all have to be the same. That's something else. They all have to be true. So the only one that's true with conjunction is the first one. All right. Go ahead. Introduce yourself to the people sitting next to you. Those are your partners. And then go ahead and write out our normal P and Q, Odie and Garfield, and then the conjunction, right in English, and then determine the truth value of each of those three statements. We do lots of group work. Two basic propositions and then conjunction propositions. All right. So P is Odie is a dog. Oops, is a dog. Q is Garfield is a giraffe. What is P and Q? And Garfield. All right. Truth statements. Odie is a dog. True or false? Garfield is a giraffe. True or false? Odie is a dog and Garfield is a giraffe. That is false. Both of the statements forming the big one is not true, so they're not both true, so it has to be false. Questions so far? Is this making sense? Isn't this fun? Yeah, okay. Okay. One more. What do we got next? Conditional. Now the conditionals are your basic if-then statements. Oops. And it works as such. So we start off with P, Q, and then if P, then Q. Start off with our basic truth table. Oops. Statements. Statements. S-T-M-T-S. All right. What you're looking at here is sort of the result of these implications. If you start with a true statement, and that implies another true statement, then overall, that is a true statement. So if true, then true, that is true. Second line, if true, then false, that is false, right? You don't want to start with something that's true that leads you to something that is false. That's no good. So that one is false. Now the last two are a little strange. If false, then true, that statement overall is true. All right, and let's do the other one while we're at it. If false, then false, that statement overall is, that is true as well. These last two are called vacuously true. Think about the statement that is something like the following. If the men on Mars are green, then it must rain on Wednesday. The problem with the statement is there are no men on Mars, so you can't tell me anything about them. So it automatically starts off as false because it's emptiness. There's nothing there. There's no way to verify that such a statement could be true, so it must be false. It's vacuously false. Vacuous means empty, right? Like the vastness of space, right? On vacuum and all this sort of stuff. So you're starting with an empty statement, a false statement. You can't do anything with that. So since you can't contradict it, we assume it must be true because there's nothing to say that it isn't. Does that make sense? This is logic theory. It's very, very crazy. Okay. What I want you to learn about this truth table is that this is the only one that turns out to be false. It's if true, then false. That is the only one that is false. All the other ones are true. So here we could have P implies Q would be if Odie is a dog, then Garfield is a giraffe. And overall, this statement, it starts with a true statement. There it is, true. Then, the then part is a false statement. So overall, this statement is false. Starts with true, goes to false, must be false.
So if you just switch that around, it would be true?
Correct. So let's do that. So if we have Q implies P, or if Q then P, this would be if Garfield is a giraffe, then Odie is a dog. That statement would be true because the first part of the statement is false, and it doesn't matter what the second part of the statement is. Both conditionals, if they start with false, the answer is false. It's vacuous. They even call it vacuously true. Okay, so you don't even need to know what the second one is. It doesn't matter. Okay. Questions?
If we're asked, like on a quiz or a test, if the statement is true or false, we would say that it was true, even though it's actually false, because it's vacuously true.
This one is true.
Yeah.
The statement is true. Yeah. Don't confuse the sub pieces here with the value overall.
So it would still be true.
The full statement is true. Yeah. Come on now. Here we go. All right, example 7. All right, let me do one of these, and then I'll let you work with your partner on the rest of them. You have the following propositions. 99 is prime, and is Q, and P rather, and then Q is 5 squared is equal to 25. You want to write out each of these and determine if the resulting statement is true or false. So I'll do the first one. So the P statement is 99 is prime. So not P would be 99 is not prime. And 99, is that prime or composite?
Composite.
It's composite. So 99 is not prime. It is true. All right, go ahead and do the other. How many you got there? 3 or 4? 4? 4 more? Yeah. Go ahead and do these other 4 with your partner. If you don't have the notes, you can be writing these on a separate sheet of paper. Oops. Yeah. There's one more. What is it? P? It's P then Q.
What we got? 25.
Number 3? Well, now, it's an OR statement. So anytime any statement says OR statement, the whole section will There's a number 5 on there too. It's P then Q at the bottom. All right, let's check. Okay, number 2 is not Q. So that the Q statement was 5 squared equals 25. So not Q would be 5 squared is not equal to 25. Right? You can either use the symbol or you can write it out in words. Is not equal to 25. Whatever you want. And the truth value of not Q is what? That is false. Because 5 squared is 25. All right, number 3. P or Q. That would be 99 is prime or 5 squared is 25. True or false? That one is true because this one was true. All right, number 4. P and Q. That would be 99 is prime and 5 squared equals 25. True or false? That is false. In order for an AND statement to be true, both statements have to be true. The first one is false. 99 is not prime. So the whole statement can't be false. Do I have any computer science people in here? They do this a lot in computer science. And, they create conditionals. If this happens, then do this. If that happens, then do this. Well, one of the things they create is if this and this happens. And what's interesting about the way the computer runs these programs is, let's say that these were the two pieces that it was checking. It was checking if P and Q were true. What the computer will do is it'll check the first one. And if it knows it's looking for and, as soon as it finds a false statement, it jumps out of there. And it doesn't even look at the other statements. That can have serious problems with your computing program if you've designed the if statement to do other things and look at everything before it jumps out. I think that's sort of interesting. All right, the last one here is if 99 is prime, then 5 squared is equal to 25. True or false?
True.
That is true. That is vacuously true, in fact. All right. Questions over those examples? Okay. Oops. Saving. Okay. All right. Let's go on to converse and contrapositive. So converse and contrapositive affects these conditionals. So I'll write it out like this. The converse of if P then Q is if Q then P. So in the converse, you literally just switch around the if and then statements. You literally just switch those around. On a contrapositive, we've got to do a little more. The contrapositive of if P then Q is if not Q, then not P. So on the contrapositive, not only do you switch them, you negate them. All right, it's the old double switcheroo here, right? You switch them and you negate them. So if P then Q becomes if not Q then not P. Now remember, all of this is relational, right? Had this statement here not been if P then Q, if it had been, say, if R then S, then the contrapositive would be if not S, then not R, right? So it's all relational, right? It's not whatever the P and the Q are, and we need other rules for other things. No, it's all sort of positional. Let's go ahead and use our 99 and 5 squared examples. Let's write out the converse of that last statement, which was if P then Q. So the converse of if P then Q is if Q then P. Which would be if 5 squared equals 25, then 99 is prime. Is that true or false? That is false. And then let's do the contrapositive. Of P, then Q. The contrapositive is if not Q, then not P. And so it's basically the converse, but the negative of each of the parts here. So if 5 squared is not 25, then 99 is not prime. True or false? Yeah. Yeah, what kind of truth is it? It's actually vacuously true, yeah. Because the first part starts off as false, so the rest of it is true, regardless, right? The whole statement is true. It's vacuously true. All right, questions so far? Okay, so that's what you got to remember. Negation changes the truth value. Conjunction is true when at least one of the statements is true. Conjunction, and, is true when they are all true. And then conditional is always true except for the one case where it's if true, then false. In that case, it's false. All right. What we're going to do next is we're going to build larger truth tables. So here we want to build the truth table for this proposition. This is called a compound proposition because there's a lot to it. It's not P and if P then Q. Use parentheses on these things just like you would in algebra. There's groupings that you have to sort of do ahead of time and things like that. When you go to build a truth table for these things, the first thing you check is how many propositions do I have? We have 2 propositions. We have P and Q. Then I need to figure out how to build it up to the big compound proposition. You don't do it all at once. You take it step by step by step. The next piece that I would like to do is I would like to compute a column of just not P. In my 4th column, I would like to do if P, then Q. And then in the final step, I will do their conjunction. Not P and if P then Q. So you see how I sort of built it up from the smallest pieces. It's like chemistry. It's like building a molecule from atoms. You can take a little bit of this, take a little bit of that. Eventually you mix them all together and get a new compound. We'll start with our basic truth table, which is true, 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 false, false, true, and false, false. Next, we'll build up the 3rd column. I recommend that you do these by columns instead of by rows. I think you'll get more out of it if you do it by columns. In the 3rd column, we want to negate P. So I look and see what P is in this row here, this first truth value row. In the first row, P is true, so not P must be false. And then looking here, true becomes false. Third line, false becomes true. Fourth line, false becomes true. All right, so I just took each of these values in the P column and I negated them to go in the not P column. Fourth column, if P, then Q. Now, we're back to using the first column for P and the second column for Q. So, if true, then true is true or false?
True.
That is true. If true, then false is false. If false, then true. True. And if false, then false. True. So that one pretty much comes straight from our conditional table. Now for the last one, we want not P and if P, then Q. So we will use this column and this column to determine that. We don't backtrack and look at what P and Q are themselves, because we have built up something bigger that we can use to answer these. And so we go straight here and here. False and true. True or false?
False.
That is false. False and false. True or false? That is false. True and true. It's true. True and true. It's true. Some of you look lost. Let me scroll down. You eventually want to get to here. So that goes in the last column. What two propositions make up this conjunction? Not P and if P, then Q. You need to think of those as one entity each. Okay? So I need a column for each of them. I need a not P and I need an if P, then Q. I need a condition. Then you're back to, I'm just going to build up the table, starting with my propositions P and Q, and the standard, every possibility is bedded out. Okay? Now, ignoring all this, we built up not P. So not P is the opposite of P. So each of these negate over to this one. So true becomes false. Ignore the Q, right? Just ignore the Q for a second. True becomes false, true becomes false, false becomes true, false becomes true. Okay? Now ignore not P and do if P then Q with P and Q, the basic building blocks. And this is from the previous page. If true, then true, true. If true, then false is false. If false, then true is vacuously true. If false, then false was also vacuously true. So this, we know this is sort of the building blocks. Now, what we want to do is not P, so these truth values, and if P, then Q, against these. In some sense, you can think of this as different letters. We normally don't write the different letters, but you could think of this as an R and an S, and this is now R and S. And you can go through. So, now, what's the condition for an and statement to be true? They all have to be true, right? So if you're looking at it and you have any false on that row, then it's going to be false. That's it. Period. Okay? So false and true would be false because there was a false. False and false is false because there was a false. In fact, there were two of them. There were. True and true must be true. They were all true. True and true is true. They were all true. All right. Question. That's how you do it. I think you're gonna like it. I hope so. I think so. They're fun once you get to do them. Okay. Does it make sense now? Okay. Yeah, you just got to build it up. All right. What's next on the big board here? Oh, logical equivalence. Okay, here we go. All right. Now, when we have these bigger propositions, like the not P and not P and if P then Q and stuff like this, we give those other names if we want to. I said R and S. There's actually another way of doing it. It's with capital letters. All right? So be very careful that you're distinguishing between lowercase and capital letters. Those are called compound propositions. So if the compound propositions, big P and big Q, have identical truth tables. Tables. Then we say that P, big P, right, and big Q are logically equivalent. Oops. Oh dear. And the notation for that is 3 lines, right? It's like an equal sign, but 50% better. Because 3 bars instead of 2. Okay, all right. P is equivalent to Q. So essentially, it means that they both are the same, right? Let me scroll back. Look on page 4 again. Which of these propositions are logically equivalent? The last two?
Does that have to be equal?
They have to be identical. Not P and if P then Q. Given the starters here, false, false, true, true. They're identical. In other words, not P has the same effect as not P and if P then Q. They are logically equivalent. If you knew that they were logically equivalent, you wouldn't have to calculate the others. So what we write here is the following. We write not P is logically equivalent to not P and if P then Q. They're logically equivalent. All right. So again, you're looking at the truth tables, bit for bit, bit for bit. Right? False, false, true, false, false, true, true, true. That'd be a 10. If they're off and even one, that's not good. That's not good. All right, a couple more definitions. Next one is tautology. Tautology means that all entries in truth table are true. So tautology means we would end up with a column of just straight down truths. Yeah. Contradiction would be what? All entries in the truth table are false.
Does it have to be the entire truth table, or is it just?
It's that column.
Okay.
It's that column, yeah. Should I say something different here? All entries in its column in truth table. Yeah, and same thing for that one. Contradiction is they're all false. And then contingency is it's mixed. It's at least one true. At least one true and one false. And that's the only thing that can happen. Either they're all true, they're all false, or there's a mixture of them. That's it. Everything we've done so far has been what?
So is a tautology the same thing as an identity?
No. Not quite. Not quite. Because an identity would be, they were exactly the same. Tautology means that you may have some trues and falses in some column here, and the tautology is they're all true. In fact, that's what I want to do. I want to take a few minutes. I want you to work with your partner. I want you to come up with a proposition that is a tautology. Okay. Work with your partner. Try to squeeze one out of it. Squeeze out of the zone. Whoever gets it done.
Does he want like actual?
Yeah, just some keys. Whatever. Yeah. You don't know, not actually the same. Just keys and cues. Come up with a proposition that is a tautology. That if you were to create the table, this column would all be true. So you know how the previous ones, some of them were true, some of them were false. True, straight down the line. See if you can basically
So like, say this one is
well, we're not doing words. We're doing keys and cues. Okay, just do keys and cues, not words. Just come up with some proposition.
So we don't need like the long truth table like we did for
I mean, I could understand.
not like the little one.
That was crazy.
And it's long one.
Yeah, come up with some, you know, let's say like hit the index. That's close. But it's not.
Okay, so is it as simple as if P is true and Q is true? Or are we doing the more complicated one?
No, you got to cover all bases.
For the long, for like this one? The complicated like this one? Or like, no.
Something like that. But see, like, so is this one, is the last one in that column, is that a tautology? No, because it has some false in it. So you create one that would always be true. So regardless of the true or false before it.
So we could just mimic this one and figure out what would make it true. Just regular P.
Okay, I'm going to give you a hint. You can actually do this with one variable. Just P. That's your hint. You don't even have to use a key.
Oh, okay.
Right? There are ones that have two businesses. You can do it if you want. If you think about it.
I don't.
Yeah, that's the one where.
Like, I understand everything that we've done. I just understand how to do
You
it.
understand what the hint?
Can I just negate Q? Or we don't have to use Q at all?
Just don't use Q at all.
Okay.
You just use P. And do stuff with P. You gotta figure out how to change that.
We can do that.
Okay, they got mine. Who else got mine? You did it? Did it work out? Did it work out? Oh, you don't have to use that.
Is that what he wants?
Actual. Just keep it. Yeah, because it's college.
Not really.
It's sort of So you're saying like P and not P. That's the thing. We're not using active. So P is a proposition. It could be true or false. The influence is false. All right. What was
How that works is not
That's very good. Very good. Let's do that in a second. All right, what did y'all get in the back?
P and P.
What? If P,
If P, then P.
then P.
Can you show us one where Q is in there?
I don't know if I can do it all. I'll try. All right, so let's see. So you have P. What are the two possibilities for the starting values of P? True or false? So then P is P. And if you want to see it really, here, I'll do another. You don't have to do this. You do it on the P row here. P column. So if P, then, if true, then true is true. If false, doesn't matter what this one is, it's vacuously true. That is a tautology. That is a tautology. They're all true. What did you come up with?
P and P.
P and P, right? If, let's see, no if here. Yeah, P and P. So true and true is true. False and false is false. So P and P is not a tautology. P or P is the same one. What do you got there?
P or not P.
Yeah, not P. That's what you need not P. And then if we do or, P or not P, well, what does the not P do? It's going to provide me with one of the true statements where the other one would have been false. So I'm always guaranteed to have a true statement here. All right? So P or not P, this would be true or false, which is true. This one would be false or true, which is true. We have a tautology. Okay. What do you got to do to make that a contradiction? What's the contradiction?
Not P's.
P and not P. Yeah, P and not P. How can something be true and false at the same time? You can't. So true and false would be false. False and true would be false. They're all false. That's a contradiction. I don't know of one offhand that has two letters, but I'm sure there's one as well. Well, we may hit one. Maybe we'll hit one here in a second. Okay. All right, so let's finish this up here. Last topic for the day is logical implication. Okay. There we go. We say that P logically implies Q if whenever P is true, Q is true. And the notation is P, a sort of a double bar arrow goes to Q. All right, so logical implication is sort of a bigger version of conditionals. It's really a if P then Q type scenario. Technically, you have logical implication if you have the P is true implying the Q is true. What you are omitting is the other three cases. Well, the other three cases are when P is true and Q is false. Under an if-then statement, under a conditional, that would be false anyway, so that's out. The other two statements that are not represented by true, true are false, true, and false, false. Well, those are vacuously true. So in many ways, I just think of this as sort of a really big if-then statement. If P, then Q, and I treat it as such, and then look everything else out here. Okay. All right. Example 10. Construct the truth table to determine the logical implication. Not P implies if P, then Q. So let's go ahead and work up the truth table here. So we have P, Q, not P, and P implies Q. If P, then Q. We'll start with our standard true, 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 false, false, true, false, false. Not P would then be false, false, true, true. And then if P, then Q, well, we have if true, then true, that's true. If true, then false, that is false. If false, then true, it's true. And if false, then false, that is also true. Now, you are looking for logical implication, meaning if the one on the left is true, does that also imply that the one on the right is true? That would be starting here and starting here. This is the big P, this is the big Q, and we're looking for P implies Q, big P implies big Q, like so. Again, you can ignore the falses because under the if statement, those imply true anyway. So this one checks out and this one checks out just because they're false. You really only have to check the true statements. This true, does it imply another true statement? Yes. And this true, does it lead to this other truth statement? Yes. So the logical implication is true. What would have happened if if this had messed up, is somewhere in this column you would have had true, and somewhere in the same row it would have been false, true leading to false. Then that would have killed it.